Hello. After studying low pass filter, let us now see how a high pass filter works and what is the response of a high pass filter. Okay, so let us start with the first order. So first order high pass filter. So again we are talking about active filters, that means we are using active components such as op amp or transistor, but in our example we will take op amp. So first order high pass filter. So low pass filter was realized using resistor, capacitor and op amp. Here also we will use resistor and capacitor itself, but thing is that we will swap its position. Okay, so the circuit diagram will be so again non-inverting configuration we are considering. So this one is grounded, R1 feedback resistor RF. Now here we have to write first capacitor then resistor. In the low pass filter, in place of capacitor we had resistor, in place of resistor we had capacitor. Now we just swapped it. Okay, so V in, and we will call this as V2 and this one is V1 and this is V out. Now let us see what is the transfer function or output voltage or the gain what we get here. So this is a non-inverting operational amplifier. So V0 is 1 plus RF divided by R1 times V2. Whatever voltage you apply at the non-inverting terminal, it will be amplified by this factor 1 plus RF by R1. Okay, so but we have to find what is V2, because we are not directly feeding our V in at the non-inverting terminal, we are passing it through a capacitor and we have to find that. So V2, if you apply the voltage divider rule, V2 voltage at this one, let me write this one R and C, voltage at V2 is nothing but the voltage across R. So that is nothing but we can write V in, the total voltage divided by the current passing through this. So current passing through this means it will be impedance offered by capacitance is 1 by j omega C plus R. This is the current flowing through this resistor. Total voltage, that is V in divided by total resistance, and we know that current inside this will be 0. There is no current passing through here, only current passes through this. So current we have written V in divided by 1 plus j omega C plus R into resistor. If we do, we will get the voltage. So into R. Okay, so let us simplify this one. So if we take common denominator, so this will be V in and j omega RC you will get at the numerator, and here you will get 1 plus j omega RC. Okay, so this is what you get for V2. V2 is V in into j omega RC divided by 1 plus j omega RC. So if we call this one as 1 and this one as 2, now you substitute this one in, substitute 2 in 1. Okay, so that is nothing but V0 is nothing but 1 plus RF by R1 divided multiplied by V2. V2 is nothing but V in j omega RC divided by 1 plus j omega RC. Okay, so this we can write in a simpler way. So how we can write this, V0 is equal to, or V0 divided by V in we will take, that is the input voltage. Instead of writing 1 plus RF by R1, I will simply write AF, I will write, and omega is nothing but omega is 2 pi RC. Okay, So j omega RC, how we can write? So j omega RC is nothing but j into 2 pi RC. Okay. So here 2 pi f, sorry, f I forgot, 2 pi f omega is equal to 2 pi f, not 2 pi RC, it is 2 pi f. Let me rub it. Let me rewrite. So omega is 2 pi f. So j omega RF means 2 pi f RC. So we will keep this j here and f we will keep, then remaining is 2 pi RC. That I can write divided by, like this, I can write 1 by 2 pi RC. Both are same. Instead of writing j 2 pi f RC, I can write jf divided by 1 by 2 pi RC. So this will go to the numerator and you will get same. So this I can again replace jf divided by this one, I will write it as fl. Since it is a high pass filter, the cutoff frequency we will call fl. We will see while seeing the graph, while we plot the graph, we will see why it is fl. So this will be V in j omega RC, I can write j f by fl, and again 1 plus j f by fl, okay, where fl is nothing but 1 by 2 pi RC, okay, and AF is 1 plus RF by R1. Okay. So now if we want to find magnitude of this, so magnitude of this will be V naught by V in. We know that it is nothing but 1 plus square root of real part square plus imaginary part square. So that will be 1 by 1 means here the gain is not 1, it is AF. So AF f by FL, that is the numerator, and denominator we get 1 plus f by FL whole square under square root. This is what we get the magnitude. AF as it is, j of f by FL magnitude is f by FL. The bottom is what you have to do is real part and imaginary part both you have. So what you have to do is square of real part plus square of imaginary part under the square root. So that is the gain. So this you know, I think you have studied in the maths also how to find magnitude of a complex number. Now we will solve one problem now. Okay, we will solve one problem. The question is like this: design a high pass filter with a cutoff frequency, 1 minute before writing this, I have to show the frequency response of this will be how. So if you plot frequency response, so in the linear scale first we will see, then we will see semi-log sheet. Okay, so this is nothing but V naught by V in magnitude that you plot versus frequency. So what you get is, you will get this is maximum frequency, maximum, that is we gain maximum. I will write G max, I will write G max, that is the maximum gain, and at cutoff frequency, that is FL. Now you see why we called it FL, because it is the high pass filter, it is the lower cutoff frequency. After that all the frequencies it will pass, that's why it is called high pass filter. And cutoff frequency we will give the suffix L because it is a lower possible. So before this, any signal if you apply with this frequency lesser than FL, it will not be passed, the gain will be very poor. So at this point this will be 707. And now if you plot in the dB scale, this roll off here, whatever we are getting roll off in the dB scale, it will be minus 20 dB per decade. So that means every decade, every multiple of 10 frequency, if you consider, this is plus, sorry, not minus, it is plus, gain will increase at the rate of 20 dB per decade. So that is what you will get in the decade scale, not in the linear scale. Okay. So in this the problem, we will plot that one, you will come to know how it is. So let me come back to this problem. Design a high pass filter with a cutoff frequency of 1 kilohertz with pass band gain 2, gain of 2, and plot the response, and plot the response. So how to solve this? We know FH is 1 kilohertz, and let us consider first C. Let C be, we have to choose the value, that is 0.01 microfarad. Any value you can choose. Usually less than or equal to 1 microfarad is preferred. Now what you have to do, you have to find formula, not it is FH, sorry, the FL it is, 1 minute. This one is FL, I have to write. So FL. Okay. So now you have the formula, FL is 1 by 2 pi RC. So I want R in this, so R equal to 1 by 2 pi FC. So F we know, F means here L, FLC. So we know the form, all the values. 2 pi FL is 1000, and capacitor is 0.01, that is 10 power minus 8. So if you do this, you will get the R value 15.8 kilo ohm you will get. Okay. So in the design means you have to find only R. C value we will assume, R value we will find. And we know that gain is 2. So gain 2 means you should know that AF is 2. So that is nothing but 1 plus RF by R1 is equal to 2. So RF by R1 is equal to 1. So that means RF equal to R1, we will take one value 10 kilo ohm. Let this is select a value you have to select, we will take 10 kilo ohm. Okay. So general value is 10 kilo ohm, so we will take 10 kilo ohm. Now we have designed this circuit. That means design means, remember this is the circuit. Design here means what is R1, what is RF, what is C, and what is R. All the 4 values you have to find. That is nothing but the design. So that itself we have done here. You can see we have found C we assumed, R we found, R1 and RF also we know now. Now let us plot the response. For that we will use this formula, V naught by V in. So that is nothing but AF F by FL and whole divided by under the square root of 1 plus F by FL to the power of 2. This formula we have to use, and we will make a tabular column. So first one is the frequency we will take, then we will find V naught by V in magnitude, and next one we will write 20 log, because usually frequency response we will plot in semi-log sheet, where y-axis is 20 log of the gain and x-axis is frequency, but it is not linear, it will be in the decade scale or decade scale. That means it is not 1, 2, 3, 4 like this division. You will have 1, 10, 100, 1000, 10,000 like this, multiples of 10. So each unit will have multiples of 10. So we will see that one, 20 log V naught by V in. So V naught by V in. Okay. So we will calculate this one. We will start with the F100. So 100 means, let me write here, this one is 100. So 100 means you have to substitute in this this one. So here we know FL is 1K and AF is 2. You substitute for each F and you will get the V naught by V in. So we will get here 0.20 we will get, and if you convert that one in the this one, what I call 20 log scale, so you will get minus 14.02. You just substitute and find, you will get that. Next one is the 200. So 200 we will get 0.39. So this will be minus 8.13. Similarly, you take for other values. 400 if you take, it will be 0.74. Remember, at 1 kilohertz is the cutoff frequency. That means it will allow the frequency above 1 kilo. So since it is 400 less than the cutoff frequency, you are not getting the gain. So minus 2.58. And 700 if you take 700, your gain will be 1.15, and in the dB scale this will be 1.19. This will be 1.19. And the next one is 1000. If you take 1000, that means 1 kilo cutoff frequency, your output will be output voltage or gain will be 1.9, and dB scale it is minus 5.56. Then 7000 if you take, this will be 1.98, and your this gain will be 5.93. And similarly, let me add one page. Okay, so similarly 7000, then 10k, if you take 10k, then this will be 1.99, and your gain will be 5.98. And finally 30k we will take. 30k, this will be 2, and this will be 6.02, and 100k if you take, this will be 2, this will be 6.02. So now you listen what we did. We first written F, then V naught by V in, then 20 log V naught V in. Now we have to plot this one. So plot means this is y axis and this is x axis. I think we need minus also here, minus sign also we need. So let us take sufficient. Okay, now here logarithmic scale means this is F. So logarithmic scale means let it be this one 10, next unit will be 100, and next it will be 1000, next unit will be 10k, next will be 100k. This is what the unit, each unit represents multiple of 10. And here we will write 20 log V naught by V in. This is what we will plot here. Okay, so we will start with this. So at 100 it is minus 14.02. So at 100, so if this is 10 minus 10 and it is minus 20 if you take, so it will be at 100, the value will be at 100, the value will be, what is the value that minus 14.02. so minus 14.02 means this value, let it be this. Next one, at 200 you have minus 8. 200 means here only we have to take 200, so minus 8, it will be somewhere here. And at 400 minus 2.58, 400 it is still near minus 2 point. Next 700 1.19, 700 1.1, 700 means approximately here, this value will be this. And at 1k, at 1k you are getting 5.56. so let me write, this is 10, this is 20, this is 30 dB, and at 1k you are getting a gain of what is that gain? At 1k it is 5.56 you are getting. So 5.56 means not here, it will be or let me rub this, we will keep scale a bit. We will take, I think let it be, this is 10 so that you can see properly, 20, 30. Okay. So at 1k this will be 5 point. So I think this is what we can take, 5 point at 1k. At 1k 5.56, at 7k 5.93. 7 means approximately here, 7 point this. Then 10k 5.98. No, it is sorry, scale is all nearby 5 point, so it is not this much above you will get almost nearby this only 5. So you will get at 7k it is this, and at 10k it is 5.98, almost this. So this value I am taking. Okay. So and after that 100k, if it is, you can see at 30k also 6.02, 100k also it is almost constant, it is constant. So you will get a graph, this is the graph you are going to get. So it is, graph is, if you plot, so this one thing you have to observe, at cutoff frequency what is the gain. So at cutoff frequency, that is 1k your gain is 5.56. At cutoff frequency, sorry, not over 5 point, it is a 3.56. Sorry, this is 3.56. So I have to, it is at the cutoff frequency. Cutoff frequency is approximately here, it is 3.56, and after the at maximum gain it will give 6. So one thing you have to observe, from 1k to at cutoff frequency your gain is, at cutoff frequency your gain is maximum minus 3 dB. This is the gain. Maximum is gain 6, but you are getting 3.56. So maximum, approximately maximum minus 3 dB gain you are getting at 1k. And next 10k, one decade if you see, there is no change in the, because after cutoff frequency it will reach the maximum value. At 30k also you are getting 6.2. That's why you are getting a flat response. So you can see here, after this it will be flat. That is what we want. It's a high pass filter. After 1k it should allow all the frequency. So its gain is constant. But this roll off we have to observe. If you observe the roll off, just see from 100 to 1k, what is the jump? That is minus 14, it is a 3.56. So almost it is a 20 dB gain. So one decade 20 dB gain you are getting, because order of the filter is 1. So the roll off rate is plus 20 dB per decade. So that one you have to observe. One is, this is flat response, flat at the pass band, and in the stop band roll off, the roll off rate is plus 20 dB per decade. Okay. So this is how you obtain a response of a first order filter. Okay. Thank you.